Okay, so we move on to the entire Carnot cycle now. So we calculated the individual heat changes, internal energy changes, and the work done in each of these 4 steps. Now we'll be trying to calculate the entire Carnot cycle. So what's the dE of the entire Carnot cycle? What's the Q of the entire Carnot cycle? And what's the W of the entire Carnot cycle? Before we move, in the lecture, there was a typographical mistake in which the W2 that we calculated was mistakenly written TH minus TC, which should be T final minus the T initial. So this is the correct one. So in your notes, kindly correct that, because the W2 and the E2 both should be like in bracket, it's T final minus T initial. So the T final was basically the colder temperature. It moved from TH to TC. So this should be the case. So having said that, let's try and calculate what the dE of the entire thing is. Before even calculating, we know what the dE for a cyclic process is. It's actually 0. Why? Because it's a state function. So you started from A, you came back to A, the dE should be equal to 0. Now, let's try and see if that's true, because you see E1 and E3 are 0, so that's fine. Now let's see if the what's the value of E2 and E4. So you see this is CV Tc minus Th, and this is Th minus Tc. So basically E2 and E4 are just negatives of each other. So this cancels this, and when you do a sum of all these 4, you get a value of 0, right? Which is true because it's a state function. When you went through a complete cycle, you got a 0. Now let's try and find out what the value of the work is when you do a summation of the work. Okay, so let's take W1, which is R TH ln VB by VA plus W2, which is minus CV TC minus TH plus W3 R TC ln VD by VC plus W4, which is minus CV TH minus TC. Now, if you look closely, minus CV TC minus TH minus CV TH minus TC. So basically, these two cancel out, right? These two values cancel out. So what we are left with is this R TH T subscript H ln VB by VA RTC called ln VD by VC. Now, this is VB by VA, this is VD by VC. If we can find out a relationship between these two, then it would be really good. Okay, so let's try and find out a relationship between these 4 variables. Now, if you see this, this is VB VA. Okay, this is VB VA, and this is, so if you see this process, the step 2, so step 2 is an adiabatic process, and step 4 is also an adiabatic process. Now, for an adiabatic process, so if I draw in here, this is V, this is P. So if you have an adiabatic process from here to here, this is VA, VD, this was TH, and this was TC, right? So in this whole process, it was TC, in this whole process it was TH, right? A, temperature at A and temperature at B are TH, temperature at C and temperature at D are TC. So for this, we know that there is a relationship between temperature and volume when we have an adiabatic process, right? So the relationship, the general relationship is like this, V1 by V2 gamma minus 1. Now T2, so if this is this process, the T2 is basically TH So Th by Tc is equal to, what is V1? V1 is here, this is not Va, this is Vd. So this is Vd by Va gamma minus 1. So this is one of these equations. And there was another process that was happening here, right? So this was Vb, this was Vc, this was Th, this was Tc. Okay? So we'll do the same thing for here. So this one is one of these equations that we'll use. And for that, the T2 by T1. So what is T2? The Tc. T1 is Th. V1. V1 is Vb. And what is V2? It is Vc. Gamma minus 1. Okay? So if you revert this to bring to equate this and this, so if this is Th by Tc, this becomes Vc by Vb gamma minus 1. Okay, so you see Th by Tc is equal to Vc by Vb gamma minus 1, Vd by Va gamma minus 1. That means, what that means is Vd by Va is equal to Vc by Vb. Okay, now can we use this to solve something over here? Okay, so we have Vd by Vc. Okay, so let me check what kind of substitutions did I do. Okay, so I'm keeping Vb by Va. I'm trying to change Vd by Vc. So what is Vd by Vc? So Vd by Vc is equal to Va by Vb. Okay, we'll be using this there. Okay, all right. Vd by Vc is Va by Vb. Okay, so this then becomes R Th ln Vb by Va, which was as it is, minus this becomes RTC. So this is plus, sorry, this is plus RTC Vd by Vc. So Vd by Vc is equal to Va by Vb. Va by Vb. Okay. Now you see that this is interchanged in these two. So to interchange that, what I have to do is I just have to, if I change this, this becomes ln Vb by Va. So now I can take out this whole thing common. So now what is common in here is R ln Vb by Va, R ln Vb by Va. So I take this R ln Vb by Va in brackets T hot minus T cold. So this is the expression for the total amount of work done. Okay, so this was the total amount of work done in this whole Carnot cycle. Okay, so we got dE, we got W, and what's the net amount of heat that was in that was exchanged, right? So that there should be something like Q, right? So we have the Q's in here, right? We have the Q. So there was just two isothermal expressions, isothermal processes in which heat was exchanged. One was QH and the other, in this case, it was QC, right? So heat was supplied and heat was ejected out in that case, okay? So you can get to you can also get exact values in terms of the Q's. So let me change the board. So in here, the Q net becomes Q1 plus Q2 plus Q3 plus Q4, right? So Q1 was basically QH, right? Q2 was an adiabatic process, this was 0. Q3 was basically heat that was released, right? And Q4 was again 0. So this net came out to be, so there was some heat supplied, and in this third step, the third step being the isothermal compression, this was compression. So work was done on the system, right? So you did work on the system. So your work done was on the system, which was negative, and Q3 also became negative. And when Q3 becomes negative, that means Q amount of heat was released out, right? So if that was released out, it should have a negative connotation, right? So that is included in here. So QH minus QC. This is the Q net of the system, okay? So let me number these, sorry. Let me number this as 42. 43, okay, the Q net. Okay, so we also have the net internal energy that was equal to 0. So we have Q net, you have E net, the change in internal energy, and you have the W. Now, the whole process of this exercise, the whole logic of this exercise was to find out the efficiency of the system, right? So what is basically the thermal efficiency of this Carnot cycle? So the thermal efficiency of the Carnot cycle, which is denoted by eta, is basically the W versus the heat that you supplied, right? The heat that you supplied. So you want to know how much heat you supplied. You do not want to know how much heat was the net heat. You don't want that. You want to know how much heat that you put in, the QH, that was the heat that was pushed in, and in response to that, what was the amount of work done, okay? Now the work obtained. Now this is heat input and this is work obtained. So I'll just write work obtained. Now, what is the amount of work obtained? We calculated in here. The net amount of is this. Okay, so I'll just copy that. R ln VB by VA times TC minus TH minus TC. Okay, and what was the amount of heat that was given in? That the amount of heat that was given in was Q input, right? And what is that Q input? That is the Q, the first Q, right? This was the heat that was given. And what is the value of that? RTH ln VB by VA, right? RTH ln VB by VA. So these things cancel out, and what remain is this. So this is the value of the efficiency. So now when we have calculated this becomes really important, because now we can understand certain things about the heat, the thermal efficiency of the Carnot cycle. We now understand that this efficiency cannot be more than 1. That means for this to be 1, the T heat and T cold has to be same, right? So that's no point of doing that, right? So if that is the case, there is no, like, the Carnot cycle is not there. So TC, so this cannot be this whole value cannot be greater than 1. So it has to be less than 1. And that is why less than 1 means that it cannot be as high as 100%. 1 means 100%, so it cannot be 100%. It has to be less than 1. Okay. Now, the efficiency is proportional to this. So the efficiency is proportional to the difference between the T hot and the T cold. So when you increase this difference, your efficiency will increase, right? And your N is inversely proportional to the T hot, right? So if you have more T hot, your efficiency is going to decrease, okay? So these are the two very important things that are coming out of this equation, that the efficiency is only dependent on these two things, the difference between T hot and T cold, and is inversely proportional to the T hot. So if you reduce the T hot, you get more efficiency. If you increase the T hot, you get less efficiency. The third thing that comes out is N is not dependent on the nature of the gas, on the type of gas, the type of gas. It did not depend. So you don't see any term related to CV or CP or things like that. So since CV is representative of a particular material, that if you had a CV term somewhere in here, we would have thought that, okay, the CV of different materials will be different, and different materials therefore affects the efficiency, which is not the case in here. There is no CV term in the final thermal efficiency. Therefore, the efficiency, the thermal efficiency of the Carnot cycle is not dependent on the nature of the gas or the type of the gas in here. Okay, so the only way to increase the efficiency is to manipulate these two things. Okay, now whatever this value turns out to be, okay, whatever this value turns out to be for that system, say if it is 0.59, okay, if that is the case, then that doesn't mean that you will be able to reach 0.59, so 59% efficiency. That does not mean, okay, 59% is the efficiency of the Carnot cycle. If the efficiency of the Carnot cycle is 59%, whatever you do, you will not be able to reach this high, because Carnot cycle is hypothetical. Everything that is happening in a Carnot cycle is reversible. There is no energy loss and things like that. Even then, you are not able to get as high as 100%. You have to keep that in mind. Okay, even Carnot cycle, which is the best case scenario, cannot get to 100%. It can get to something, say like 59%. Okay, now if the Carnot cycle efficiency is 59%, you can get as high as this, but no greater than this for that system. Okay, that is the meaning of a Carnot cycle. No matter how well you do this, you cannot get better thermal efficiency than the Carnot cycle. That is the whole deal with this Carnot cycle efficiency.